Hello students, we'll see how to derive work done during an adiabatic process in thermodynamics today. If a process is adiabatic, then no heat exchange takes place during that process between the system and the surroundings. The system generally comprises of an ideal gas present in a closed container. Okay, so no heat exchange will take place. Equation for adiabatic process is P into V raised to gamma equals constant. This is the equation we'll be using to find out work done. But before finding the work done, let's look at the equation. P into V raised to gamma equal to constant. Constant can be taken as, say, K, just a symbol to denote it. So I can write P equals K upon V to the power gamma. This will help us sketch the PV diagram for adiabatic process. Now, as volume is increased, pressure will decrease non-linearly. So this is how graph of adiabatic process should look like. In this case, I have indicated adiabatic expansion of an ideal gas. Okay. Now we can mark the parameters. In state 1, with pressure will be P1 and here volume be V1. Similarly, these are the parameters in state 2, and because the process is adiabatic, so P1 into V1 to the power gamma equals P2 into V2 to the power gamma. Here gamma is adiabatic exponent. Gamma equals Cp by Cv and its value depends on the type of gas taken. Okay. Now we'll try to find out work done during an adiabatic process. I hope everyone knows to evaluate work done. This is the expression we use, integral P dV from initial state to the final state. In this process, adiabatic process, P into V raised to gamma is constant, say K. So P can be written as K into V to the power minus gamma. So in this integral, I'll replace this pressure with this expression. So taking the constant out of integral, if you know from mathematics, this is how we integrate x to the power n if n is not equal to minus 1. Then this is the result valid. I can use the result here. And then we put in the limits v1 to v2. Okay. So we'll be getting K into V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma divided by 1 minus gamma. This is what we get. Okay, I'll drop a part here to write further. Okay, so I can take this K inside and write like this. Now this K is, if you remember, we have taken P into V raised to gamma equal to constant K. So K is equal to the value of this expression throughout the adiabatic process. So it is equal to P1 into V1 to the power gamma. It is also equal to P2 into V2 to the power gamma. So I can put K as either this expression or that expression. So here in the first term, I will be using K equal to P2 into V2 to the power gamma. And in the second term, I'll be using this expression for K, as it will give us a simplified expression. This simplifies to P2 into V2 minus P1 into V1 upon 1 minus gamma. This is work done during an adiabatic process by an ideal gas. This P2 V2 minus P1 V1 can also be written as nR delta T if required. So we can use either this expression or this expression to find out work done by natural gas during adiabatic process. Okay, thank you.